Okay, I want to tell you about a really cool discovery that used the interference that we've been talking about with light. Okay, you'll have to look up do a Google search or something like that for gravitational waves, and you'll learn that on February 11th of 2016, a 100-year-old theory by Einstein was verified experimentally. Okay, it's something that validates theory of relativity in an amazing way, and it's one of the most precise measurements that mankind has ever made. So precise that when Einstein had theorized the experiment that could be done to prove his theory, he got really sad, he got depressed, because he thought that mankind could never achieve such a precise measurement. And we did. We're amazing. We should be very proud of ourselves. Okay, so this is what it is. You'll have to look into the details for the gravitational waves, but the experiment, it can be understood from the basic interference that we've been studying. So what is called is an interferometer. The experiment is called an interferometer. So basically consider this. We have light. Okay, we have light coming in, some laser light, coherent lights coming into a system. And what we have is we have a mirror here that is called a half-silvered mirror. Okay, what that means is instead of being reflecting all the light like your mirror at home would, it is kind of partially silvered so that some light passes through but some reflects. So we get some of this light reflects off and goes that way while some goes through. Okay, look at this direction. And remembering that this is coherent light, that means that, let's say, when all these photons got to this point, they were, had some certain phase, and let's say they changed phase by one cycle right here, maybe traveling some set distance. If they travel that same set distance over here, they have the same phase. So the phase here would be the same as the phase right here. Okay. So what we then do is we shoot one of these off and let it hit a mirror some distance away. Now this is a fully silvered mirror, so the light hits it, and bounces off. I'm going to offset it a little bit just so we can see the rays. And it bounces off and comes back to this mirror. Alright? Now technically, some of the light bounces off and goes this way, and we're not going to worry about that much. But some of it, again, passes through. Okay? Alright, this light, we do the same thing. We put a mirror over here. Okay, it's a fully silvered mirror, so this light goes, hits the mirror. Okay, I'm going to offset it again. Passes through, comes back, and some of that light passes through this mirror going this way, and I'm not going to worry about that light, but some of it reflects and comes this way. Alright? Now, I hope you're seeing that what we've done is we now have path differences between these photons. At this moment, as they're coming along, at that moment, they're all in phase. But now, this has traveled this distance, coming back to here, and this has traveled this distance, coming back to here. Now, if this distance, okay, let's call this, if this distance here, let's call this D1, is the same as this distance here, we'll call that D2. If those are the same, then these in-phase photons travel this distance, they've reached some new phase, but these have reached that same new phase, and so the light here is now in phase, and if we put a detector right here, there's a detector, we'd get a bright spot. Okay? So that doesn't sound too cool of itself. We could have done that, just shine the light straight across and we've gotten a bright spot. But this is where it's cool. If I move this mirror, 1/4 of a wavelength, just 1/4 of a wavelength, okay? I move that mirror 1/4 of a wavelength of whatever light's being used here. Suddenly, the total path difference, which is 2 times D2, because I go this far and back again, that means the path difference now, my delta R, is now twice this distance I moved it, because I had to go a 1/4 wavelength more and a 1/4 wavelength back. So now it has a total path difference of a half a wavelength. So by moving this one, keeping this one set, moving this one a quarter wavelength further meant that this returning light is now a half wavelength different than the original light, and when they combine here, we're going to get a dark spot. So this would give me a dark spot on the mirror. Okay. Now that would give a complete dark spot, and this device is called an interferometer. I can move this in small increments to affect a change in the intensity on the screen. And to move at a quarter wavelength, I'd go from all the way bright to all the way dark. Now we can create some pretty good detectors that can measure to a good precision very low light levels or very small differences in light levels. And so I can tell if this thing moves even a small fraction of a wavelength because the light intensity here will change slightly. Okay? And so what they did is they fine-tuned this experiment so well, creating super good detectors that can detect super small differences in light, and having these mirrors be super nicely polished. I'm using the word super a lot. It's just awesome. We're all super. Okay? But they were able to actually detect a movement of a mirror different than the other mirror, so relative movement, I should say, of less than the width of a proton. A single proton, they could detect that motion because of how well they could detect a change in light here from that extra path difference. Okay, so it didn't go all the way dark, it just got less than, or changed from what it was before, because the slight interference, the slight destructive interference. And with that, they were able to detect this motion that was the smallest or smallest distance measurement that we've made. And that was necessary to detect the change in the space around us that was necessary to detect gravitational waves. So again, the details of that, I'm going to leave you to go see some of the news broadcasts that were made at the time, the announcements, and some of the theory on Wikipedia. You can find it out. Some really cool stuff. Pretty complex math for a lot of the details, but this experimental apparatus is understood even in just a Physics 2 class. We can understand how they took the measurement, the most precise measurement mankind has made in just this Physics 2 class using basic principles of waves. I hope you thought that was cool. I think it's totally amazing.